Look up at the night sky from a dark place, far from city lights, and you may see a faint, misty band stretching from horizon to horizon. It looks like a cloud, a river of pale light scattered across the darkness. For thousands of years, humans called it the Milky Way, imagining it as spilled milk or a celestial path. Only recently did we understand what it truly is. We are looking at the inside of our own galaxy. That soft glow is the combined light of hundreds of billions of stars, all bound together by gravity, all orbiting a common center, all part of a vast cosmic structure that we inhabit but cannot see from the outside. The Milky Way is not just a collection of stars. It is a gravitational ecosystem, a dynamic, evolving island universe more than 100,000 light-years across. And like all things in the cosmos, it has a past, a present, and a future. To understand the fate of the Milky Way, we must first understand what it is. Our galaxy is a barred spiral galaxy, meaning it has a flat rotating disk with spiral arms and a central elongated bar of stars. The disk is thin compared to its diameter, only a few thousand light-years thick but stretching tens of thousands of light-years from side to side. Within that disk lie spiral arms regions where gas and stars are slightly denser, forming sweeping patterns that wrap around the galactic center. These arms are not solid structures like the arms of a pinwheel. They are density waves, areas where gas is compressed as it orbits, triggering bursts of star formation. They are regions of birth and brilliance, where massive young stars illuminate surrounding gas clouds and carve out glowing nebulae. Our Sun resides in one of these spiral arms, known as the Orion Arm or local spur, roughly 27,000 light-years from the galactic center. We are not near the edge, nor near the center. We occupy a quiet suburb of the Milky Way, orbiting the center once every 230 million years at a speed of about 220 kilometers per second. As the Sun moves through the galaxy, it carries the entire solar system with it, planets, comets, asteroids, and Earth itself, sweeping around the core in a long, slow journey that began long before life emerged and will continue long after humanity is gone. At the heart of the Milky Way lies something extraordinary, a supermassive black hole known as Sagittarius A. It contains about 4 million times the mass of our Sun, compressed into a region no larger than our solar system. Though it is currently quiet, not actively consuming large amounts of matter, it exerts an enormous gravitational influence on the stars in the galactic core. Astronomers have tracked the orbits of stars whipping around this invisible center at tremendous speeds, confirming its existence. This black hole is not an anomaly. Almost every large galaxy in the universe appears to host a supermassive black hole at its center. The Milky Way's core is therefore not just a crowded cluster of stars. It is anchored by one of the most extreme objects known. But the visible stars and gas tell only part of the story. Surrounding the Milky Way is a vast halo of dark matter, an invisible substance that does not emit or absorb light, yet exerts gravitational pull. Dark matter outweighs all the visible matter in the galaxy by a significant factor. Without it, the galaxy would not hold together the way it does. The rotation speeds of stars in the outer regions reveal that there must be far more mass than we can see. This dark halo extends far beyond the bright disk, reaching perhaps hundreds of thousands of light years into space. It forms the gravitational scaffold that binds the galaxy and shapes its evolution. The Milky Way is not alone in space. It is part of a small collection of galaxies known as the Local Group. The largest members are the Milky Way and the Andromeda Galaxy, also known as M31. Andromeda is slightly larger and more massive than our own galaxy, and it lies about 2.5 million light-years away. In addition to these giants, dozens of smaller dwarf galaxies orbit both. Some of these dwarfs are being torn apart by gravitational forces, their stars stretched into streams that wrap around the Milky Way. Galactic evolution is not a solitary process. It is shaped by interactions, mergers, and accretion events that slowly reshape structure over billions of years. If we could step outside the Milky Way and view it from afar, we would see a magnificent spiral galaxy, glowing with the light of hundreds of billions of stars. Bright young clusters would mark the spiral arms. Dark lanes of dust would trace the interstellar medium. A central bulge of older stars would dominate the core. The bar structure would stretch across the center, channeling gas inward and influencing star formation. Yet the galaxy would not appear static. Stars orbit continuously. Gas flows. New stars are born in cold, molecular clouds. Old stars die, some gently, some violently, in supernova explosions that scatter heavy elements into space. Star formation is the lifeblood of the galaxy. Within the spiral arms, clouds of hydrogen gas collapse under gravity to form new stars. Massive stars burn brightly and die young, enriching the surrounding medium with elements forged in their cores. Smaller stars live longer, quietly fusing hydrogen for billions of years. Over time, the galaxy recycles material. Gas becomes stars. Stars produce heavier elements, and stellar winds and supernovae return enriched gas to the interstellar medium. This ongoing cycle shapes the chemical evolution of the Milky Way, gradually increasing the abundance of elements like carbon, oxygen, silicon, and iron elements essential for planets and life. The Milky Way's structure reflects its history. Its disk contains stars of varying ages, with younger populations in the spiral arms and older stars in the thicker disk and central bulge. The halo contains ancient stars, some of the oldest in the galaxy, orbiting in elongated paths that reflect early formation processes and past mergers. Stellar streams reveal remnants of dwarf galaxies that were absorbed long ago. The Milky Way has grown over time by cannibalizing smaller galaxies, incorporating their stars and gas into its own structure. This hierarchical growth is a common feature of galactic evolution throughout the universe. The current star formation rate of the Milky Way is modest, about 1 to 2 solar masses per year. That means roughly 1 or 2 new sun-sized stars are formed each year on average. This rate has fluctuated over cosmic time. In the past, the Milky Way may have formed stars more rapidly. As gas supplies diminish and stellar feedback heats and disperses clouds, star formation gradually slows. The galaxy is not a perpetual fountain of new stars. It depends on the availability of cold gas. Over billions of years, as gas is consumed and expelled, star formation will decline. Yet the Milky Way is still dynamic. Supernova explosions continue to punctuate the disk. Pulsars spin in distant regions. Black holes feed intermittently. Massive star clusters carve bubbles in the interstellar medium. Cosmic rays zip through the galaxy, guided by magnetic fields. The galactic center occasionally shows signs of past activity, with enormous gamma-ray structures known as the Fermi bubbles extending above and below the disk. These structures hint that Sagittarius A times may have been more active in the past, perhaps consuming matter and launching jets millions of years ago. The Sun's journey around the galaxy is not entirely smooth. As it orbits, it passes through spiral arms, moves above and below the galactic plane, and encounters varying densities of gas and stars. Some scientists speculate that these motions may influence comet influx from the Oort cloud or affect cosmic ray exposure on Earth. While such effects remain under investigation, they illustrate that our local environment is part of a larger galactic dance. To grasp the fate of the Milky Way, it is crucial to recognize that galaxies are not eternal in their current forms. They evolve. Over billions of years, interactions with neighboring galaxies reshape them. Gas inflows and outflows alter their composition. Central black holes grow and influence star formation. Spiral structures can fade or transform. The Milky Way we see today is a snapshot in a long process of change. The Andromeda Galaxy is moving toward us at about 110 kilometers per second. Though the distance is immense, gravity is drawing the two galaxies together. In roughly 4 to 5 billion years, they will collide. This is not a collision in the everyday sense. The stars within each galaxy are so far apart that direct stellar collisions will be rare. Instead, the two galaxies will pass through one another, their gravitational fields distorting their shapes, flinging stars into new orbits, compressing gas clouds, and triggering bursts of star formation. Over time, repeated interactions will merge them into a single, larger galaxy. This future merger is one of the most significant events in the Milky Way's destiny. But that lies ahead. For now, the Milky Way continues its steady rotation. It continues forming stars, hosting planetary systems, and evolving quietly on timescales far longer than human civilization. Its fate is tied to gravity, dark matter, stellar life cycles, and cosmic expansion. The forces that built it are the same forces that will eventually reshape it. The Milky Way is not just a background for our existence. It is a participant in a grand cosmic narrative. It was born from primordial fluctuations in the early universe, grew by merging with smaller galaxies, and continues to evolve through star formation and gravitational interactions. It contains the raw materials for life and the engines that produce light. It is both our home and a transient structure in an expanding cosmos. Understanding its future requires understanding the forces that govern it. Gravity binds it and will draw it into merger. Electromagnetism governs its luminous processes and interstellar medium. The strong force shapes the nuclear reactions inside its stars. The weak force governs decay and stellar fusion pathways. Together, these forces determine not only what the Milky Way is, but what it will become. The night sky's pale band is not static. It is a dynamic, living system of stars, gas, dust, dark matter, and black holes. Its current form is temporary. Over billions of years, its spiral arms will shift, its star formation will wane, its central black hole may grow, and its structure will transform through interaction with Andromeda. The Milky Way's fate is written not in myth or prophecy, but in physics, universal laws acting patiently across cosmic time. The Milky Way is not a static island of stars frozen in place. It is a living system governed by time. Every star inside it is aging. Every cloud of gas is drifting, cooling, or collapsing. Every orbit is subtly shifting under gravity. To understand the fate of our galaxy, we must first understand its clock. That clock does not tick in seconds or centuries. It ticks in millions and billions of years. Galaxies evolve slowly, almost imperceptibly on human timescales, yet over cosmic ages, they transform completely. The Milky Way we see today is not the Milky Way that existed 5 billion years ago, and it will not resemble the Milky Way 5 billion years from now. A galaxy's evolution is powered by a simple but profound cycle. Gas becomes stars. Stars forge elements. Stars die and return enriched material to space, and that material forms new stars. This stellar life cycle drives the long-term changes in brightness, structure, and chemistry within the galaxy. The Milky Way is currently a spiral galaxy rich in gas and dust, still actively forming new stars at a rate of roughly 1 to 3 solar masses per year. That may sound small compared to the galaxy's total mass, but over billions of years, this steady pace reshapes the stellar population and alters the composition of interstellar space. At the heart of this evolution lies hydrogen, the simplest and most abundant element in the universe. Hydrogen clouds drift through the galaxy, often in cold, dense molecular form. When gravity pulls these clouds together, new stars ignite. In their cores, hydrogen fuses into helium, releasing energy that allows stars to shine for millions to billions of years. But fusion also changes composition. Over time, stars build heavier elements: carbon, oxygen, silicon, iron. When stars die, especially in supernova explosions, these elements are scattered back into the galaxy. The next generation of stars forms from gas that is slightly more enriched than before. This process of chemical enrichment is gradual but relentless. Early in the Milky Way's history, the galaxy contained mostly hydrogen and helium left over from the Big Bang. There were no heavy elements. The first stars were likely massive and short-lived, burning hot and dying violently. Their supernovae seeded the galaxy with the first heavier elements. With each generation, the abundance of metals, astronomical shorthand for elements heavier than helium, increased. Today, our solar system contains iron in its core, oxygen in its water, carbon in its life. All of it was forged in earlier stars. The galactic clock is therefore chemical as well as luminous. Younger stars tend to contain higher metallicity because they formed from gas enriched by previous generations. Older stars preserve the chemical fingerprints of earlier eras. By studying stellar composition, astronomers can reconstruct the Milky Way's past. Some stars in the halo of our galaxy are more than 12 billion years old. They formed when the Milky Way was young and chaotic, assembling from smaller protogalactic fragments. Others, like our Sun, formed in a more stable disk environment enriched by countless earlier supernovae. Star formation itself is not constant. It fluctuates. In the Milky Way's early history, star formation was likely more intense, fueled by abundant gas and frequent mergers with smaller galaxies. Over time, as gas reservoirs diminished and supernova feedback heated and dispersed material, the rate of star formation declined. The galaxy gradually matured. Today, the Milky Way is considered a moderately active star-forming galaxy. It is neither a violent starburst galaxy nor a quiet, quiescent elliptical. It sits somewhere in between, a stable spiral, still forming stars, but at a modest pace. This gradual decline is inevitable. The Milky Way's supply of cold gas is finite. Star formation consumes hydrogen and locks it into stellar cores. While some material is recycled through stellar winds and supernovae, not all gas returns in a form suitable for immediate star formation. Some is ejected into the galactic halo or beyond. Some remains too hot or diffuse to collapse again. Over billions of years, the balance shifts. Star formation slows. The galaxy's bright blue spiral arms, dominated by short-lived massive stars, begin to fade as fewer new massive stars are born. Massive stars live fast and die young. They burn through their fuel quickly and explode as supernovae within millions of years. Their deaths inject energy and heavy elements into the interstellar medium. They also generate shock waves that can trigger new star formation nearby. In this way, stellar death can promote stellar birth. Yet the cycle cannot continue indefinitely. As the gas supply thins, there are fewer clouds dense enough to collapse. The galaxy's spiral arms gradually lose their youthful brilliance. Meanwhile, smaller stars dominate the long-term future. Red dwarfs, which are smaller and cooler than the Sun, are the most common type of star in the Milky Way. They burn their hydrogen fuel extremely slowly, with lifespans extending into trillions of years, far longer than the current age of the universe. Even as star formation declines, existing red dwarfs will continue shining. The Milky Way's brightness will change character. Instead of brilliant, massive blue stars lighting the spiral arms, long-lived red dwarfs will provide a steady but dimmer glow. The galactic clock is also gravitational. Stars orbit the center of the Milky Way in a vast disk, roughly 100,000 light-years across. The Sun takes about 230 million years to complete one orbit. Over billions of years, stars drift through the spiral arms, encounter giant molecular clouds, and experience gravitational perturbations. These interactions slowly alter their orbits. The disk itself can warp and ripple due to interactions with satellite galaxies and dark matter substructures. The Milky Way is not rigid. It breathes and flexes over time. Our galaxy is also not alone. It is surrounded by dozens of smaller satellite galaxies, including the large and small Magellanic Clouds. These satellites orbit the Milky Way and occasionally pass close enough to disturb its disk. Tidal forces can stretch and strip material from these smaller galaxies, adding stars and gas to the Milky Way. In fact, evidence suggests that the Milky Way has grown significantly through mergers with smaller galaxies in its past. Stellar, streams-long, thin arcs of stars trace the remnants of these ancient collisions. Each merger injects new material and energy into the galaxy. It can trigger bursts of star formation by compressing gas. It can thicken the galactic disk or contribute to the formation of the stellar halo. The Milky Way's history is written in these interactions. It is not a closed system evolving in isolation. It exchanges matter with its surroundings, slowly building mass through accretion and mergers. Dark matter provides the invisible scaffolding for this evolution. The Milky Way is embedded in a massive halo of dark matter that extends far beyond its visible disk. This halo influences how stars and gas move. It shapes the galaxy's rotation curve and provides the gravitational well that binds satellite galaxies. Over time, dark matter subhalos can interact with the disk, causing ripples and heating stellar populations. Though unseen, dark matter is central to the galaxy's long-term stability and evolution. As billions of years pass, the Milky Way's spiral structure itself may change. Spiral arms are not permanent fixtures. They are density waves moving through the disk. Stars drift in and out of these arms. If star formation slows significantly, the contrast between arms and interarm regions may fade. The galaxy could gradually transition into a more featureless disk before its eventual merger with Andromeda reshapes it entirely. The Sun's lifetime is also tied to the galactic clock. Formed about 4.6 billion years ago, it is roughly halfway through its main sequence life. In about 5 billion years, the Sun will exhaust hydrogen in its core and expand into a red giant. This event will occur during a period of galactic change, possibly near the time of the Milky Way's interaction with Andromeda. The solar system's fate is therefore intertwined with the broader fate of the galaxy. Yet even without dramatic collisions, the Milky Way's evolution continues quietly. White dwarfs accumulate as more stars end their lives. Neutron stars and black holes become part of the stellar population. Some of these compact remnants form binary systems that may eventually merge, producing gravitational waves. Others remain isolated, drifting through the galactic disk. Over time, the proportion of stellar remnants increases. The galaxy gradually becomes more populated with the ashes of past stars. Star clusters also evolve. Open clusters gradually disperse as gravitational interactions eject members. Globular clusters, older and more tightly bound, orbit the galactic halo for billions of years. Some may eventually spiral inward through dynamical friction, contributing stars to the central regions. The Milky Way's structure is therefore shaped not only by star formation, but by the slow redistribution of stars over cosmic time. As star formation declines, the interstellar medium changes. Supernova rates decrease as fewer massive stars are born. The heating of gas becomes less intense. Without strong feedback, some gas may cool and settle into new configurations, though overall star formation efficiency will drop. The galaxy slowly transitions from an active spiral into a quieter system dominated by aging stars. The Milky Way's future is not catastrophic in the near term. It is evolutionary. Over the next few billion years, it will continue forming stars, though at a declining rate. Its spiral arms will shift. Its satellites will orbit and merge. Its chemical composition will grow richer in heavy elements. Its stellar population will age. Eventually, however, a dramatic chapter awaits. The collision with the Andromeda Galaxy. But that is a story for later. Before that encounter reshapes the galaxy, the Milky Way's own internal clock will continue ticking, stars forming and dying, gas cycling, gravity sculpting structure. Galaxies are not static islands of light. They are evolving ecosystems driven by the interplay of fundamental forces. The Milky Way's present form is a snapshot in an ongoing process that began over 13 billion years ago. Understanding that process, the galactic clock, is essential to understanding what comes next. Because the fate of the Milky Way is not a sudden event. It is the accumulation of billions of small changes guided by gravity, fueled by nuclear reactions, illuminated by electromagnetism, and punctuated by occasional explosive transformations. The galaxy we call home is aging. Its stars are moving through their life cycles. Its gas reservoirs are shrinking. Its structure is shifting. Time is the most powerful force in this story. And the Milky Way's clock is still ticking. The Milky Way does not float through space alone. It is embedded in something far larger, far heavier, and almost entirely invisible. Surrounding the glowing spiral arms, the bright stellar disk, and the central bulge lies a vast halo of dark matter, a mysterious substance that neither emits nor absorbs light, yet outweighs all the visible stars and gas combined. This invisible framework is not a minor detail. It is the gravitational backbone of our galaxy. Without dark matter, the Milky Way would not hold together as it does. Its spiral arms would unravel. Its stars would move differently. Its satellites would escape. To understand the future of our galaxy, we must understand the unseen mass that shapes it from the outside in. The evidence for dark matter begins with motion. When astronomers measure how fast stars orbit the center of the Milky Way, they find something puzzling. According to Newtonian gravity, orbital speeds should decrease with distance from the center once most of the mass is enclosed. This is what happens in our solar system. Planets farther from the sun move more slowly. But in galaxies, stars far from the center move at nearly the same speed as those much closer in. The rotation curve remains flat. The only way to explain this is to conclude that there is far more mass spread throughout the galaxy than we can see. That mass does not shine. It does not reflect light. It does not interact with electromagnetic radiation in any detectable way, yet its gravitational pull is undeniable. Dark matter is not concentrated only in the galactic disk. It forms an enormous halo extending far beyond the visible edges of the Milky Way, perhaps 10 times larger than the luminous disk. This halo contains the majority of the galaxy's total mass. Estimates suggest that visible matter stars, gas, dust accounts for only about 15% of the Milky Way's total mass. The remaining 85% is dark matter. It forms a roughly spherical distribution enveloping the galaxy, influencing the motion of everything inside it. This dark halo is not smooth. It likely contains clumps and substructures, remnants of smaller dark matter halos that merged with the Milky Way over cosmic time. These subhalos may pass through the galactic disk, subtly disturbing stellar orbits and contributing to ripples and warps. Stellar streams, long trails of stars stripped from dwarf galaxies, provide indirect evidence of these dark matter structures. As satellite galaxies orbit and are torn apart by tidal forces, their stars stretch into arcs that trace gravitational interactions with the halo. The shapes and disruptions of these streams allow astronomers to map the distribution of dark matter in unprecedented detail. Dark matter's influence extends to the formation of the Milky Way itself. In the early universe, small fluctuations in density visible today in the cosmic microwave background were amplified by gravity. Regions slightly denser than average attracted more matter, growing into dark matter halos. These halos acted as gravitational wells, pulling in gas and enabling the formation of the first stars and galaxies. In this sense, dark matter formed the scaffolding upon which visible matter assembled. Without dark matter, the growth of large-scale structure would have been too slow to produce the galaxies we observe today. The Milky Way likely formed through a series of mergers and accretions. Smaller galaxies, each embedded in their own dark matter halos, collided and merged over billions of years. The stars and gas from these systems blended into the growing galactic disk and halo. The dark matter halos merged as well, creating the large halo that now surrounds the Milky Way. This hierarchical formation process is supported by both simulations and observations. The stellar halo of the Milky Way contains old stars with distinct chemical signatures, likely remnants of ancient dwarf galaxies consumed long ago. Even today, the Milky Way continues to accrete material. The Sagittarius dwarf galaxy, for example, is currently being torn apart and absorbed. Streams of its stars arc around the galaxy, marking its path. The large and small Magellanic clouds are gravitationally bound satellites whose interactions with the Milky Way distort the galactic disk. These ongoing mergers are not catastrophic. They are incremental additions to mass and structure. Over billions of years, such interactions gradually reshape the galaxy. Dark matter also governs the Milky Way's future interactions. The gravitational pull between the Milky Way and the Andromeda Galaxy, our nearest large galactic neighbor, is dominated by their dark matter halos. These halos overlap in space long before the visible disks touch. The mutual attraction will eventually draw the two galaxies together in a colossal merger billions of years from now. Without dark matter, this gravitational dance would unfold differently or not at all. The halo determines the timing and dynamics of the collision. The nature of dark matter remains one of the greatest mysteries in physics. It does not appear to consist of ordinary atoms. It does not emit or absorb light. It interacts primarily through gravity. Leading candidates include weakly interacting massive particles, WIMPs, axions, or other exotic particles not yet detected directly. Despite decades of experiments, its exact identity remains unknown, yet its gravitational fingerprints are everywhere. Dark matter's invisibility complicates observation, but gravity offers tools to probe it. Gravitational lensing, where massive objects bend the light of background galaxies, allows astronomers to map mass distribution independently of light. In galaxy clusters, lensing reveals that dark matter often lies in regions separate from hot gas after collisions, demonstrating that dark matter interacts weakly with itself and ordinary matter. In the Milky Way, subtle distortions in stellar streams can reveal the presence of dark subhalos. The galaxy is not only a stellar system, it is a laboratory for dark matter physics. As the Milky Way evolves, dark matter will continue to shape its structure. Over time, interactions between dark matter and stars can lead to dynamical heating of the disk, thickening it, and altering stellar orbits. Satellites embedded in their own halos will continue to merge, adding stars and dark matter. The halo's gravitational influence extends far beyond the visible galaxy, affecting the motion of distant objects and even intergalactic gas. The dark matter halo also plays a role in retaining gas. Its deep gravitational well helps prevent supernova-driven winds from expelling too much material into intergalactic space. In smaller galaxies with weaker halos, gas can be lost more easily, suppressing star formation. The Milky Way's substantial halo has allowed it to sustain star formation over billions of years. Yet, even this reservoir is finite. As gas is consumed and expelled, the rate of new star formation declines. Dark matter influences not only motion, but also timing. The orbital period of the Sun around the galactic center, about 230 million years, is determined by the total enclosed mass, including dark matter. Over billions of years, the Sun has completed roughly 20 orbits. Each orbit carries it through different spiral arms and environments, potentially influencing cosmic ray exposure and comet perturbations. While such effects are subtle, they illustrate how dark matter indirectly shapes local conditions. Looking far into the future, dark matter will continue to anchor the Milky Way even as star formation wanes. After the eventual merger with Andromeda, the resulting galaxy, sometimes called Milkomeda, will likely be an elliptical galaxy dominated by aging stars and a massive dark matter halo. The visible structure will change dramatically, but the dark matter will remain the dominant mass component. Over trillions of years, as stars exhaust their fuel and compact remnants accumulate, the galaxy will dim. Red dwarfs will burn slowly. White dwarfs will cool. Neutron stars and black holes will persist. Dark matter, however, will not evolve in the same way. It does not radiate or cool. It will continue orbiting and interacting gravitationally, shaping the galaxy's structure long after the last stars have faded. Some theories suggest that dark matter particles may eventually annihilate with one another, producing radiation over extremely long timescales. If this occurs, it could create faint emission in the distant future. But such processes are speculative and dependent on the particle nature of dark matter. For now, dark matter remains a silent partner in the galaxy's story. The fate of the Milky Way cannot be understood without dark matter. It determines the galaxy's mass, its rotational stability, its merger history, and its future interactions. It shapes the orbits of stars and satellites. It anchors the galaxy against the gravitational pull of neighboring systems. It formed the gravitational wells that allowed the first stars to ignite. In the cosmic timeline, dark matter emerged early, dominating the matter content of the universe long before stars and galaxies formed. It provided the gravitational scaffolding for structure formation. As baryonic matter, ordinary matter, fell into dark halos, it cooled and formed stars. The luminous universe is a visible tracer of a much larger, invisible framework. In the coming chapters, the Milky Way's evolution will lead toward collision and transformation. But even in those dramatic events, dark matter will remain the invisible architect, guiding motion and binding mass. The galaxy's fate is not merely written in stars, it is written in the unseen mass that holds them together. The Milky Way is not just a spiral of light, it is a luminous veneer wrapped around a vast halo of darkness. That darkness is not emptiness. It is structure, weight, and gravity, an unseen foundation shaping the galaxy's past and future. The Milky Way shines today with the light of hundreds of billions of stars, but that brilliance is temporary. Galaxies are not eternal beacons. They are engines that consume fuel, and like all engines, they slow when their resources dwindle. The Milky Way's long-term future is not defined by a sudden catastrophe, but by a gradual fading. Over billions of years, star formation will decline, bright blue stars will disappear, and the galaxy will grow quieter and redder. This slow dimming is a natural consequence of stellar evolution and the finite supply of gas within the galaxy. The fate of the Milky Way begins not with collision or collapse, but with the quiet exhaustion of its most vital resource, cold hydrogen gas. Star formation is the heartbeat of a spiral galaxy. Massive, short-lived stars illuminate spiral arms in brilliant blue light. Nebulae glow with ionized gas. Supernovae enrich and stir the interstellar medium. All of this activity depends on one essential ingredient: cold molecular gas. Gravity can pull gas together to form stars only if that gas is dense and cool enough to collapse. As long as the Milky Way retains a substantial reservoir of cold gas, new stars will continue to form. But gas is not infinite. Each generation of stars locks away hydrogen in stellar cores. Some of that material returns to space through stellar winds and supernovae, but not all of it remains available for future star formation. Massive stars explode, dispersing enriched gas, but they also inject energy into their surroundings, heating and dispersing clouds. Over time, more gas becomes too diffuse or too hot to collapse again. Star formation rates decline. At present, the Milky Way forms about 1 to 3 solar masses of stars each year. That rate is modest compared to starburst galaxies, which can form hundreds of solar masses per year, but it is enough to sustain a vibrant spiral structure. However, observations show that the star formation rate in the Milky Way has gradually decreased over cosmic time. Billions of years ago, the galaxy was forming stars at a much higher rate. As gas reservoirs diminished and feedback processes regulated collapse, the rate slowed. The next several billion years will likely see a continued decline. The Milky Way's cold gas supply will not vanish overnight. Gas from the galactic halo and from minor mergers may replenish some of what is consumed, but the overall trend is downward. As star formation slows, fewer massive blue stars will appear in spiral arms. These stars are short-lived, burning out in a few million years. Without them, the galaxy's bright arms will fade. Low-mass stars, particularly red dwarfs, will dominate the stellar population. Red dwarfs are small and dim compared to the Sun, but they are extraordinarily long-lived. Some may shine for trillions of years. As the Milky Way ages, its stellar population will become increasingly dominated by these small, cool stars. The galaxy's color will shift from bluish-white to redder tones as hot, massive stars become rare. The Sun itself is part of this evolution. At about 4.6 billion years old, it is roughly halfway through its stable main sequence phase. In about 5 billion years, it will exhaust hydrogen in its core and expand into a red giant. During this transformation, it will engulf the inner planets and dramatically alter the solar system. This event will occur around the same time that the Milky Way begins interacting more strongly with the Andromeda Galaxy. The fate of our solar system is therefore entwined with the broader galactic future. As star formation slows, supernova rates will also decline. Massive stars, which end their lives in supernova explosions, will become less common. The injection of heavy elements into the interstellar medium will taper off. The galactic environment will grow quieter. The interstellar medium, once churned by frequent explosions, will settle into a calmer state. Cosmic ray production from supernova remnants will decrease. White dwarfs will accumulate as more sun-like stars exhaust their fuel. These dense remnants will slowly cool over trillions of years, fading from view. Neutron stars and black holes, the remnants of massive stars, will continue to orbit within the galaxy. Some may form binaries and merge, producing gravitational waves and brief bursts of light. But overall, the frequency of dramatic stellar deaths will decrease. The Milky Way's spiral structure itself may gradually weaken. Spiral arms are maintained by density waves and ongoing star formation. If star formation becomes too low, the contrast between arms and interarm regions will diminish. The galaxy may transition into a smoother, less defined disk before its eventual merger with Andromeda reshapes it entirely. The chemical composition of the galaxy will continue to evolve, but at a slower pace. Each generation of stars enriches the interstellar medium with heavier elements. As star formation declines, enrichment slows. The metallicity of new stars will increase only marginally. The era of rapid chemical evolution will give way to a period of relative stability. Beyond star formation, gravitational dynamics will continue reshaping the galaxy. Over billions of years, stellar orbits can change through interactions with molecular clouds and dark matter substructures. The disk can thicken as stars scatter off gravitational perturbations. Stellar streams from disrupted satellites will continue to mix into the halo. The Milky Way will slowly change shape, even without major mergers. The galactic center, dominated by a supermassive black hole, will remain a gravitational anchor. Occasionally, stars will wander too close and be tidally disrupted, producing brief flares. Gas inflow toward the center may continue sporadically, igniting periods of low-level activity. But absent major accretion events, the central black hole will remain relatively quiet compared to the bright quasars seen in earlier cosmic epochs. As billions of years pass, the Milky Way will become increasingly dominated by stellar remnants and long-lived, low-mass stars. The galaxy's total luminosity will decline gradually. Its appearance will shift from a vibrant spiral to a calmer, redder system. Yet this is only one chapter in its evolution. The impending collision with Andromeda will dramatically alter this trajectory. In about 4 to 5 billion years, the two galaxies will begin to interact gravitationally. Their dark matter halos are already overlapping. As they draw closer, tidal forces will distort their disks. Star formation may briefly spike due to gas compression. Eventually, the galaxies will merge into a single elliptical-like system. But even after that collision, the story of dimming continues. The merged galaxy, often called Milkomeda, will contain a large population of aging stars and stellar remnants. Star formation may briefly increase during the merger, but afterward it will decline sharply as gas reservoirs are exhausted or heated. The spiral structure will disappear, replaced by a more spheroidal configuration. The galaxy will glow with the accumulated light of billions of old stars, gradually fading over trillions of years. On even longer timescales, the universe itself influences the galaxy's fate. As cosmic expansion accelerates due to dark energy, distant galaxies will recede beyond our observable horizon. The local group of galaxies, including Milky, will become gravitationally isolated. Over immense periods, stellar encounters and gravitational interactions may eject some stars from the galaxy. Black holes may gradually merge and dominate the mass distribution. Eventually, as stars burn out and remnants cool, the galaxy will enter a dark era, illuminated only by the faint glow of white dwarfs and the occasional flare from black hole accretion. The dimming of the Milky Way is not dramatic like a supernova. It is slow and inevitable. It reflects the fundamental reality that stars are finite. Hydrogen is finite. The processes that create light and heavy elements cannot continue forever. Gravity, nuclear physics, and electromagnetism combine to produce stars, but they also ensure that stars cannot shine indefinitely. In the grand scale of cosmic time, the Milky Way's bright spiral phase is temporary. We live during an era when star formation is still active, when massive stars still illuminate spiral arms, when supernovae still explode and enrich the galaxy. But this era will not last forever. The galaxy will grow quieter. Its color will shift. Its structure will change. It will evolve from a youthful spiral into an older, redder system. Understanding this dimming is essential to understanding the Milky Way's ultimate fate. It is not only collisions or black holes that define the future. It is the gradual transformation driven by the life cycles of stars and the steady consumption of gas. The galactic clock ticks slowly, but it never stops. The Milky Way's fate begins with this quiet fading, a long twilight that precedes more dramatic changes. And even in that fading, the fundamental forces continue their work. Gravity holds the galaxy together. Nuclear reactions sustain its stars. Electromagnetism carries their light. And over cosmic time, these forces guide the galaxy toward its next chapter. The most dramatic event in the Milky Way's future is not a supernova, not the death of the sun, and not the slow fading of its spiral arms. It is a collision, a gravitational encounter between two entire galaxies. In roughly 4 to 5 billion years, the Milky Way will begin its long, inescapable merger with the Andromeda Galaxy. This is not a distant speculation. Careful measurements of Andromeda's motion show that it is moving toward us at about 110 kilometers per second. The two galaxies are already bound by gravity. Their dark matter halos are interacting even now. The cosmic clock is counting down to a galactic collision that will reshape the local group forever. At first glance, the idea of galaxies colliding may sound catastrophic. Images of spiraling stars smashing into each other come easily to mind. But galaxies are mostly empty space. The average distance between stars is so vast that direct stellar collisions are rare even during a merger. Instead, the collision unfolds as a slow gravitational dance lasting billions of years. The true violence happens not between stars, but between gravitational fields, gas clouds, and dark matter halos. The shapes of both galaxies will stretch, distort, and interpenetrate under tidal forces. Long streams of stars will arc into intergalactic space. Gas will compress and ignite bursts of star formation. Central black holes will spiral toward one another in a titanic embrace. Andromeda, also known as M31, is slightly larger than the Milky Way. It contains roughly 1 trillion stars, about twice as many as our galaxy. Its dark matter halo is immense. As the two galaxies approach, their outer halos are already interacting gravitationally. This interaction does not produce visible fireworks, but it influences the motion of stars and satellite galaxies on the outskirts. The merger begins invisibly, long before the luminous disks touch. When the visible disks finally draw near, perhaps in about 4 billion years, the sky from Earth, if Earth still exists, will change dramatically. Andromeda, now a faint smudge visible to the naked eye, will grow larger and brighter over millions of years. Its spiral arms will stretch across the sky. Tidal forces will distort both galaxies. Stars will be flung into elongated arcs called tidal tails. These tails may extend hundreds of thousands of light years into space, forming luminous bridges and loops. The first close pass will not produce a final merger. Instead, the galaxies will likely swing past each other, slowed by gravitational interaction and dynamical friction. Dynamical friction occurs when massive objects move through a background of stars and dark matter, creating gravitational wakes that act like drag. Over time, this drag removes orbital energy, bringing the galaxies closer together. After the first encounter, the galaxies will separate slightly before gravity pulls them back for a second, more decisive collision. During these encounters, gas clouds within the galaxies will experience strong compression. When gas compresses, it can collapse under its own gravity and form new stars. The merger may trigger a period of intense star formation, a starburst. Massive young stars will form in abundance, shining brightly and living briefly. Supernova explosions will follow, enriching and stirring the interstellar medium. The merger, therefore, may briefly rejuvenate star formation even as the long-term trend of decline continues. The central supermassive black holes of both galaxies will also begin a slow inward spiral. As the galactic cores approach, the black holes will form a binary system orbiting each other at the center of the merging galaxy. Their orbital motion will gradually decay as they interact with surrounding stars and emit gravitational waves. Eventually, they will merge in a single event that releases an enormous burst of gravitational radiation far beyond anything human instruments can detect from such distances, but immense by cosmic standards. The shape of the merged galaxy will differ from both progenitors. Spiral structure depends on orderly rotation and sustained star formation. After the merger, the resulting galaxy, often nicknamed Milkomeda, will likely be an elliptical galaxy. Elliptical galaxies are more spheroidal and lack distinct spiral arms. Their stars move in more randomized orbits rather than organized disks. Much of the cold gas may be consumed or heated during the merger, reducing future star formation. The galaxy will glow with the accumulated light of older stars, appearing smoother and redder. For the solar system, the merger will be visually spectacular, but not necessarily catastrophic. Simulations suggest that the Sun's orbit may change, possibly moving farther from the galactic center. There is a small chance the solar system could be ejected into intergalactic space, but the probability is low. Stellar collisions remain unlikely due to the vast separations between stars. The greater danger to Earth will come from the Sun's own evolution into a red giant long before the merger completes. The merger with Andromeda is part of a broader pattern. The universe evolves hierarchically. Small structures merge into larger ones. Galaxies grow by accreting smaller companions. The Milky Way has already consumed numerous dwarf galaxies. Andromeda has done the same. The local group itself may eventually merge into a single massive galaxy, incorporating smaller members such as the Triangulum Galaxy. Dark matter halos play a central role in this process. The halos overlap and merge long before visible structures do. Their gravitational interaction determines the trajectory and timing of the collision. Without dark matter, the dynamics would be entirely different. The halos are vast and diffuse, extending far beyond the visible edges of galaxies. Their interaction ensures that Andromeda and the Milky Way cannot simply pass by and drift apart. The merger will also reshape the stellar halo. Streams from both galaxies will interweave, forming complex patterns. Globular clusters may be redistributed. Some stars will be flung into extended orbits far from the galactic center. Over time, gravitational relaxation will smooth these features, creating a more uniform distribution of stars. As Milky settles into equilibrium, star formation will decline sharply. Much of the gas will have been consumed or heated. Without spiral density waves to organize star-forming regions, and with diminished cold gas, the galaxy will become dominated by older stars. The bright blue stars of spiral arms will be replaced by red giants and red dwarfs. The galactic clock will continue ticking, but the rhythm will be slower and quieter. The merger will not be the final chapter. After Milky forms, gravitational interactions between stars and compact remnants will continue over trillions of years. Black holes at the center will merge and grow more massive. Occasional tidal disruptions of stars will produce flares. Stellar remnants may form binaries that merge and emit gravitational waves. But overall, the galaxy will enter a long period of decline. Eventually, as star formation ceases entirely, the galaxy will fade. White dwarfs will cool into black dwarfs. Neutron stars will cool and spin down. Black holes will dominate the mass budget. Dark matter will continue to provide gravitational structure, but luminous matter will dwindle. The galaxy will become a dim collection of aging stars and compact remnants orbiting within a vast halo. On timescales far beyond trillions of years, even more exotic processes may occur. Proton decay, if it exists, could gradually dissolve matter. Black holes may slowly evaporate through Hawking radiation over unimaginably long timescales. But these events lie so far in the future that they remain speculative within our current understanding. The Andromeda collision is therefore both dramatic and transitional. It marks the end of the Milky Way as a spiral galaxy and the beginning of a new configuration. It is a gravitational inevitability dictated by the mass distribution of the local group. Yet, it is not an explosion. It is a transformation. Galaxies are not fragile. They endure collisions and reassemble into new forms. The fate of the Milky Way is written in gravity. From its formation in the early universe, through its gradual aging, to its eventual merger with Andromeda, gravity guides its path. The collision will not erase our galaxy. It will remake it. And long after the merger, the galaxy, whatever shape it takes, will continue evolving under the same fundamental forces that have shaped it from the beginning. The sky that future observers, if any exist, will see after the merger will be different. There will be no familiar spiral band of stars across the night. Instead, there may be a diffuse glow of a giant elliptical galaxy filling the heavens. The local group will stand alone in an expanding universe where distant galaxies have receded beyond view. The Milky Way's fate is not annihilation but transformation. It is part of the cosmic pattern of growth and change. Stars are born and die. Galaxies collide and merge. Structures form, dissolve, and reform. The forces that built the Milky Way will continue shaping its destiny. And as the Andromeda Galaxy draws ever closer, silently and inexorably, the future of our cosmic home approaches, not with sudden catastrophe, but with the steady, patient pull of gravity guiding two great galaxies toward their shared destiny. When galaxies collide, the word collision can be misleading. There is no single explosive moment, no universal fireball, no instant of total destruction. Instead, a galactic merger is a prolonged gravitational ballet that unfolds over hundreds of millions to billions of years. Stars rarely crash into one another because the distances between them are so vast. But gravity does not need direct contact to reshape entire systems. During a galactic merger, gravity stretches, twists, compresses, and redistributes billions of stars, immense clouds of gas, dark matter halos, and even supermassive black holes. It is one of the most powerful large-scale transformations in the universe. When the Milky Way and Andromeda begin their first close approach, their visible disks will still be intact, but tidal forces will already be at work. Tidal forces arise because gravity pulls more strongly on the nearer side of an object than on the farther side. In everyday life, tidal forces from the moon and sun cause Earth's oceans to rise and fall. In a galactic encounter, tidal forces act across tens of thousands of light years. As Andromeda approaches, its gravitational field will tug more strongly on the side of the Milky Way closest to it. The far side will feel a slightly weaker pull. The difference is enough to stretch the galaxy into elongated shapes. Spiral arms will distort and extend into long tidal tails, arcing streams of stars pulled out into intergalactic space. These tidal tails can stretch for hundreds of thousands of light years. They are not simply decorative features. They are evidence of angular momentum redistribution. Gravity transfers orbital energy and angular momentum between the two galaxies, reshaping their structures. Some stars will be flung into extended orbits. Others will sink toward the center. The elegant symmetry of spiral patterns will dissolve into chaotic arcs. Gas clouds respond even more dramatically than stars. Unlike stars, which move like collisionless particles in most galactic encounters, gas clouds can collide and compress. When two galaxies interpenetrate, their interstellar media do not pass through each other quietly. Clouds slam together, Shock waves ripple outward, and gas is compressed to densities high enough to trigger intense star formation. These bursts of starbirth, known as starbursts, can briefly increase the rate of star formation by orders of magnitude. Massive blue stars will ignite in abundance, shining brightly but living only a few million years before exploding as supernovae. The merger can therefore briefly rejuvenate both galaxies with new stellar light. This starburst phase is both creative and destructive. The new massive stars generate powerful stellar winds and ultraviolet radiation, ionizing surrounding gas. Soon after, supernova explosions inject enormous amounts of energy into the interstellar medium. These explosions can drive galactic winds, expelling gas into the halo or beyond. The very process that creates new stars can also accelerate the depletion of the remaining gas. In this way, mergers can hasten the long-term decline of star formation by consuming and dispersing the fuel needed for future generations. As the Milky Way and Andromeda pass through one another for the first time, their dark matter halos will already have merged significantly. Dark matter halos are vast and diffuse, extending far beyond visible stars. When they overlap, gravitational interactions between them slow the galaxy's motion through a process called dynamical friction. As a massive galaxy moves through the dark matter halo of another, it gravitationally perturbs the halo particles, creating a wake of increased density behind it. This wake exerts a gravitational pull opposite the direction of motion, gradually draining orbital energy. Dynamical friction ensures that the two galaxies cannot simply swing past each other and escape. Instead, they will be drawn into repeated passes, each one bringing them closer. After the first encounter, the galaxies will separate slightly, pulled apart by their residual orbital momentum, but gravity will pull them back together. The second pass will likely be even more violent, with stronger tidal distortions and more gas compression. Spiral arms may be shredded completely. Star clusters could be thrown into unusual orbits. Stellar streams will form and overlap. The once distinct identities of the Milky Way and Andromeda will blur. The central supermassive black holes of both galaxies, Sagittarius A times in the Milky Way and Andromeda's central black hole, which is several times more massive, will begin a slow inward journey toward one another. At first, they will orbit independently within the merging stellar cores. As the cores combine, the black holes will form a gravitationally bound binary system. Surrounding stars will interact with this binary, stealing energy and momentum, allowing the black holes to spiral closer. Eventually, when their separation becomes small enough, gravitational wave emission will dominate the energy loss. The two black holes will merge in a single event that releases enormous energy in the form of gravitational waves. The black hole merger will not destroy the galaxy. It will create a more massive central black hole and possibly produce a burst of electromagnetic radiation if gas is present nearby. In some mergers observed elsewhere in the universe, the combined black hole can be kicked slightly by asymmetric gravitational wave emission, shifting its position relative to the galactic center. Such a recoil is unlikely to eject the central black hole entirely in a massive system like Milky, but it could cause temporary displacement. By the time the merger is complete, likely several billion years after the first encounter, the resulting galaxy will bear little resemblance to its spiral ancestors. Instead of two thin rotating disks, the stars will settle into a more spheroidal distribution. The orderly rotation that once maintained spiral arms will be replaced by more random stellar orbits. This is how elliptical galaxies form, through major mergers that scramble stellar motions and erase spiral structure. The new galaxy, sometimes called Milkomeda, will likely be classified as a giant elliptical galaxy. Elliptical galaxies are generally redder and contain older stellar populations than spirals. They have little cold gas and minimal ongoing star formation. Their stars move in more chaotic orbits, giving the galaxy a smooth, featureless appearance. The merger will have consumed or heated much of the available gas, leaving little fuel for sustained new star formation. For any surviving planetary systems, the merger will alter the night sky dramatically, but not necessarily cause immediate destruction. The probability of direct stellar collisions is extremely low. The average distance between stars is measured in trillions of kilometers. Even during the densest phases of the merger, stars will typically pass far apart. However, gravitational interactions could alter stellar orbits. Some stars may be flung into distant trajectories. Others may sink closer to the galactic center. The Sun, if it still exists at that time, could find itself in a new region of the galaxy. The merger will also influence the local group as a whole. Smaller galaxies like the Triangulum Galaxy may be drawn into the gravitational interplay, eventually merging with Milkomeda as well. Over time, the local group will coalesce into a single massive galaxy surrounded by a common dark matter halo. Once the merger settles, star formation will likely decline rapidly. Without the rotating disk and spiral density waves that concentrate gas into star-forming regions, and with much of the gas consumed or expelled, Milkomeda will enter a more quiescent phase. The brilliant blue stars of spiral arms will be gone. The galaxy will glow primarily with the light of older red stars and long-lived red dwarfs. As billions more years pass, even those stars will age. Massive stars will already be extinct. Sun-like stars will become red giants and then white dwarfs. Only small red dwarfs will remain active, shining dimly for trillions of years. The galaxy's luminosity will steadily decrease. White dwarfs will cool and fade into black dwarfs' cold, dark remnants that emit almost no light. Neutron stars and black holes will continue orbiting in the gravitational web of the merged galaxy. The universe itself will also evolve during this time. Due to dark energy, cosmic expansion will accelerate. Distant galaxies beyond the local group will recede faster and eventually disappear beyond our observable horizon. From within Milkomeda, the night sky will grow emptier as external galaxies fade from view. The local group will become an isolated island in an expanding cosmic ocean. On time scales far beyond trillions of years, gravitational interactions within Milkomeda will continue. Stars may slowly escape the galaxy due to cumulative gravitational perturbations. Stellar remnants could occasionally merge, producing gravitational wave events. The central supermassive black hole may accrete remaining gas or consume passing stars in tidal disruption events, creating rare bursts of radiation. But overall, activity will decline. The galaxy will enter a dark, quiet era. Eventually, only compact remnants and black holes will dominate the mass of Milkomeda. Over unimaginable timescales, even black holes may evaporate through Hawking radiation, though this process would take far longer than the current age of the universe by many orders of magnitude. The final stages of galactic evolution extend into a time so distant that it challenges comprehension. The collision of the Milky Way and Andromeda is therefore not an end, but a transformation. It marks the end of spiral structure and the beginning of a massive elliptical galaxy. It triggers bursts of star formation and then ushers in a long decline. It merges central black holes and reshapes stellar orbits. It turns two familiar galaxies into a single new entity. Galactic mergers are common in the universe. Many elliptical galaxies we observe today were formed from similar collisions in the past. The Milky Way's fate is not unique. It follows the same gravitational script written across cosmic history. Gravity brings structures together. Over time, mergers create larger and more massive systems. The universe evolves hierarchically. From our present vantage point, the Andromeda collision lies billions of years in the future. It will occur long after humanity's current era. Yet its inevitability is written in the motions we measure today. The faint shift in Andromeda's position against background galaxies reveals its approach. The gravitational pull between our galaxies cannot be denied. The dance has already begun. When galaxies collide, they do not simply smash, they transform. They exchange material, trigger new creation, and ultimately settle into new forms. The Milky Way's destiny is not destruction, but metamorphosis. It will lose its spiral identity and gain a new one as part of a larger, merged galaxy. In the vast scale of cosmic time, this event is both immense and routine. It is a reminder that nothing in the universe is permanent. Not stars, not galaxies, not even the structures we consider stable. Gravity's pull reshapes everything given enough time. The Milky Way's future is not quiet stasis. It is motion, interaction, and eventual union. And when that union is complete, a new galaxy will emerge, carrying within it the stars, remnants, and history of two once separate worlds, bound forever by gravity's relentless force. When the Milky Way and Andromeda finally complete their long gravitational dance, the result will not be a chaotic ruin, but a new, unified galaxy, an object astronomers sometimes call Milky. This new galaxy will be larger, more massive, and structurally different from either of its progenitors. The elegant spiral arms that once defined both galaxies will be gone. In their place will be a vast elliptical structure filled with aging stars, stellar remnants, and an even more massive central black hole. The birth of Milky Way marks not just the merging of two galaxies, but the transformation of an entire galactic identity. Spiral galaxies like the Milky Way are defined by their rotating disks and ongoing star formation. Their bright arms trace regions of active stellar birth, lit by massive blue stars. But spiral structure depends on order on a thin disk of stars and gas rotating coherently around a central mass. When two large spiral galaxies collide and merge, that orderly rotation is disrupted. The gravitational forces involved scramble stellar orbits, converting organized disk motion into a more random distribution. The first close pass between the Milky Way and Andromeda will stretch and distort both galaxies. Spiral arms will twist into elongated tidal tails. Some stars will be flung outward into intergalactic space, forming luminous arcs that wrap around the merging system. Others will fall inward toward the combined center of mass. As the galaxies pass through each other and separate, their shapes will be profoundly altered. But the most dramatic restructuring will occur during the final coalescence. As the galactic cores approach one another, their gravitational influence becomes dominant. The central regions, rich in stars and possibly gas, will merge. Stellar orbits will become increasingly chaotic. Instead of following nearly circular paths in a disk, stars will move in elliptical and random trajectories around the new center. Over time, this randomization smooths the structure into a spheroidal shape characteristic of elliptical galaxies. Elliptical galaxies differ from spirals in several key ways. They lack well-defined spiral arms. They contain little cold gas. Star formation rates are low. Their stellar populations are dominated by older, redder stars. In many ellipticals, most star formation ceased long ago. Milky is expected to resemble such a system after the merger stabilizes. During the merger, however, there may be a temporary spike in star formation. The compression of gas during the collision can ignite bursts of stellar birth. These star bursts will produce large numbers of massive stars that shine brightly and die quickly. For a few 100 million years, the merging galaxy may appear unusually luminous, but this burst will consume remaining cold gas rapidly. Once the gas reservoir is depleted or heated, star formation will decline sharply. The merging of the two supermassive black holes will be another defining moment. Sagittarius A, the Milky Way's central black hole, and Andromeda's central black hole will form a binary system in the heart of Milkomeda. Over time, gravitational interactions with surrounding stars will shrink their orbit. Eventually, gravitational waves will carry away sufficient energy for the black holes to merge. The final merger will release a powerful burst of gravitational radiation, briefly outshining all other gravitational wave sources in the universe. After the merger, the new, more massive black hole will settle at the center of Milkomeda. Its mass may be several times that of Sagittarius A. If sufficient gas remains nearby, it could accrete material and shine as an active galactic nucleus for a time. However, because much of the gas will have been consumed or expelled during the merger, the central black hole may remain relatively quiet. The stellar halo of Milkomeda will also change. The halos of both progenitor galaxies, composed of older stars and globular clusters, will combine. Stellar streams from disrupted satellites will weave together into a complex structure. Over billions of years, gravitational relaxation will smooth these features, producing a more uniform distribution. The dark matter halos of both galaxies will have merged long before the visible disks. The resulting halo will be enormous, encompassing the combined mass of the local group. Dark matter will continue to dominate the galaxy's total mass. Its gravitational influence will shape the orbits of stars and satellites within Milkomeda. For the solar system, if it survives the sun's red giant phase, the view of the sky will be transformed. The familiar band of the Milky Way will be gone. Instead, the night sky may glow with a more diffuse, elliptical brightness. The stellar density near the solar system may change, depending on its new orbit. Some simulations suggest that the Sun could be flung into a more distant orbit around the merged galaxy's outskirts. Others indicate it may remain within the inner regions. In either case, direct stellar collisions remain unlikely due to vast separations between stars. The Triangulum Galaxy, M33, another member of the local group, may also merge with Milkomeda eventually. Its fate depends on its orbital dynamics during the Milky Way-Andromeda interaction. If captured, its stars and dark matter will be incorporated into the growing elliptical galaxy. Over time, the local group will coalesce into a single massive system. Once the merger is complete and star formation subsides, Milkomeda will enter a long period of aging. Massive stars will vanish within millions of years. Sun-like stars will evolve into red giants and then white dwarfs over billions of years. Only long-lived red dwarfs will remain active. The galaxy's color will shift toward red as its stellar population ages. White dwarfs will cool and dim, eventually becoming black dwarfs, hypothetical objects that have cooled so much they emit almost no light. Neutron stars and stellar mass black holes will continue orbiting silently. Occasionally, binary systems may merge, producing bursts of gravitational waves or gamma rays. But overall, the galaxy will grow quieter. As the universe expands under the influence of dark energy, distant galaxies will recede beyond the observable horizon. From within Milkomeda, observers in the far future may see only their own galaxy and perhaps a few nearby remnants. The cosmic microwave background will redshift to undetectable wavelengths. The large-scale structure of the universe will become invisible. Milkomeda will appear isolated in an increasingly dark cosmos. Over trillions of years, gravitational interactions within Milkomeda may eject some stars into intergalactic space. These runaway stars will drift into darkness. Stellar remnants may slowly sink toward the center through dynamical friction. Black holes may merge, gradually increasing the mass of the central black hole. These processes are slow but inevitable. On timescales far exceeding trillions of years, more speculative events may occur. If protons are unstable and decay over extremely long timescales, matter itself could gradually disintegrate. Black holes may eventually evaporate via Hawking radiation, though this would require timescales vastly longer than the current age of the universe. Such events belong to the distant, almost unimaginable future. The birth of Milkomeda represents a turning point. It is the moment when two great spiral galaxies surrender their distinct forms and become something new. It is a testament to gravity's power to reshape structures on the grandest scales. It also marks the beginning of the end of active star formation in our local cosmic neighborhood. Yet even in its fading, Milkomeda will remain a monument to cosmic evolution. Its stars will carry the chemical signatures of billions of years of stellar life cycles. Its central black hole will embody the history of mergers and accretion. Its dark matter halo will preserve the gravitational memory of the local group's assembly. Galactic mergers are not violent in the way supernovae are violent. They are patient transformations, unfolding over epochs. They demonstrate that even vast structures like galaxies are not permanent. They are shaped by gravity's relentless pull and by the availability of fuel for star formation. The Milky Way's future as Milkomeda is not a disaster story. It is an evolution story. It reflects the natural progression of structure in a universe governed by gravity. The spiral arms that define our galaxy today are temporary patterns in a much longer narrative. In the end, Milkomeda will shine softly with the light of aging stars, a massive elliptical galaxy adrift in an expanding universe. Its birth will have been one of the greatest transformations in local cosmic history. Its existence will remind future observers, if any remain, that galaxies, like stars, are born, evolve, and transform under the same fundamental forces that govern all of existence. The fate of the Milky Way is therefore not a sudden destruction, but a long metamorphosis. It will change shape, change brightness, and change structure. It will merge, settle, and fade. And through it all, gravity will remain the guiding force, weaving two galaxies into one and shaping the next chapter of our cosmic home. Long before the Milky Way finishes merging with Andromeda, long before the galaxy settles into a new elliptical form, the most immediate chapter of our cosmic future will unfold much closer to home. The fate of the Milky Way is inseparable from the fate of its stars, and for us, the most important of those stars is the Sunday. The Sun is not eternal. It is a middle-aged star, steadily converting hydrogen into helium in its core. It has been doing so for about 4.6 billion years, and it has enough fuel to continue for roughly another 5 billion. But its future is already written in the physics of gravity and nuclear fusion. The same forces that ignited it will eventually transform it, reshape the solar system, and determine whether any trace of Earth survives. The Sun today is in a stable phase known as the main sequence. In this stage, gravity compresses the core inward, while the pressure from nuclear fusion pushes outward. Hydrogen nuclei fuse into helium through a chain of reactions governed by the strong and weak nuclear forces. The energy released radiates outward through the Sun's layers, eventually reaching the surface and streaming into space as sunlight. This balanced hydrostatic equilibrium has kept the Sun steady for billions of years. But the Sun is not static even now. With every second, it converts about 600 million tons of hydrogen into helium. The helium accumulates in the core, gradually changing its composition. As helium builds up, the core slowly contracts under gravity. Hydrogen fusion continues in a shell around the helium core, but the core itself no longer produces energy once hydrogen is depleted there. This process happens gradually, but it has consequences. As the core contracts, it heats up. That heat increases the rate of fusion in the surrounding shell, which increases the Sun's overall luminosity. In fact, the Sun today is about 30% brighter than it was when it first formed. This increase is subtle on human timescales, but profound over geological time. Billions of years ago, Earth's climate was shaped by a fainter Sunday. In the distant future, a brighter sun will alter planetary conditions long before the red giant phase begins. In roughly 1 billion years, The sun's increasing luminosity will significantly affect Earth's climate. As the sun brightens, more energy will reach Earth's surface. Oceans may begin to evaporate more rapidly. Water vapor, a greenhouse gas, will accumulate in the atmosphere, trapping additional heat. This positive feedback could lead to a runaway greenhouse effect, similar to what happened on Venus. Long before the sun becomes a red giant, Earth may lose its oceans and become inhospitable to life as we know it. The planet's surface temperature will rise, and complex life may not survive. The sun's transformation accelerates as hydrogen in the core is exhausted. In about 5 billion years, core hydrogen fusion will cease entirely. Without fusion pressure to balance gravity, the helium core will contract more rapidly. As it contracts, it heats up dramatically. Meanwhile, hydrogen fusion in a surrounding shell intensifies, increasing the sun's luminosity further. The outer layers respond by expanding. The sun will swell into a red giant, growing perhaps 100 times larger in radius than it is today. As a red giant, the sun's outer atmosphere will extend outward beyond the current orbit of Mercury and possibly engulf Venus and Earth. The exact fate of Earth is uncertain, but tidal interactions and drag within the sun's extended atmosphere could cause Earth to spiral inward and be consumed. Even if Earth somehow avoids direct engulfment, its surface will be scorched beyond recognition. The oceans will be long gone, the crust melted, and any remnants of life erased. The transformation into a red giant is not the end. As the helium core continues to contract and heat, it will eventually reach temperatures high enough for helium fusion to begin. This stage, known as the helium flash in stars like the Sun, ignites helium into carbon and oxygen through the triple alpha process. The Sun will enter a brief period of renewed equilibrium, burning helium in its core and hydrogen in a shell. But this phase is short-lived compared to the main sequence. Once helium is exhausted in the core, the Sun lacks the mass required to fuse heavier elements like carbon. The core will contract again, while the outer layers expand further into a more luminous red giant stage known as the asymptotic giant branch. Strong stellar winds will blow off the outer layers, creating expanding shells of gas illuminated by ultraviolet radiation from the hot core. These shells form a planetary nebula, a glowing cloud marking the Sun's final shedding of mass. At the center of this nebula will remain a white dwarf, the Sun's exposed core. Roughly half the Sun's current mass will remain in this compact remnant, about the size of Earth but containing immense density. The white dwarf will no longer produce energy through fusion. It will glow from residual heat, gradually cooling over billions of years. Eventually, it will fade into a cold, dark remnant, sometimes called a black dwarf, though none yet exist because the universe is not old enough. The transformation of the Sun will dramatically reshape the solar system. As the Sun loses mass through stellar winds, its gravitational pull will weaken. The remaining planets' orbits will expand outward. Mars, Jupiter, Saturn, and the outer planets will drift into wider orbits. Asteroid belts and comet clouds may be destabilized. Some objects could be ejected entirely. The Kuiper belt and Oort cloud may be perturbed by both solar mass loss and galactic tidal forces. Even beyond the Sun's death, the solar system will not remain unchanged. Over billions of years, passing stars and molecular clouds can perturb distant objects in the Oort cloud, sending comets inward or ejecting them into interstellar space. The gravitational environment of the Milky Way will continue to influence the solar system's architecture. After the merger with Andromeda, stellar densities in certain regions may increase, slightly raising the chance of close stellar encounters. Though direct collisions remain unlikely, gravitational interactions could alter planetary orbits over immense timescales. The merger of the Milky Way and Andromeda will likely occur around the same time that the Sun becomes a red giant. From Earth's perspective, if Earth still existed, the sky would be spectacular. Andromeda would stretch across the heavens, and tidal distortions would warp the galactic disk. But these grand galactic changes will be overshadowed locally by the Sun's transformation. The fate of Earth will be sealed by solar evolution long before the galactic merger completes. As the solar system ages further, the white dwarf Sun will remain as a faint ember. The outer planets, perhaps intact, will orbit a cooling stellar corpse. Jupiter and Saturn may retain their atmospheres, though they will receive far less energy. Icy moons in the outer system may briefly warm during the red giant phase but then refreeze. Over trillions of years, the white dwarf will cool and darken. Planets may gradually spiral outward due to interactions with passing stars and gravitational tides from the galactic environment. Eventually, the Milky Way itself will no longer resemble a spiral galaxy. After merging with Andromeda, it will likely be an elliptical system dominated by old stars. Star formation will decline sharply as gas is consumed or heated. The galaxy will become redder and dimmer. In the distant future, the night sky within Milkomeda will contain few new stars. Most will be long-lived red dwarfs or compact remnants. The Sun's white dwarf remnant will be just one of countless stellar corpses orbiting within a vast dark matter halo. On even longer timescales, trillions to quadrillions of years, stellar remnants will dominate. Red dwarfs will eventually exhaust their fuel. White dwarfs will cool. Neutron stars and black holes will persist. Some white dwarfs in binary systems may collide and explode as type Ia supernova long after normal star formation has ceased. Black holes at the centers of merged galaxies will continue to interact and perhaps merge again if additional structures fall inward. Beyond that lies an era where gravitational interactions slowly scatter stars and remnants. Over time, galaxies may lose stars to intergalactic space through cumulative gravitational perturbations. Milkomeda may gradually evaporate as individual stars gain enough energy to escape. Black holes may slowly sink toward the center through dynamical friction, merging into even larger central black holes. Eventually, if protons are unstable and decay, a process not yet observed but predicted in some grand unified theories, even atomic matter may slowly dissolve. White dwarfs and neutron stars could gradually disintegrate into subatomic particles. If proton decay does not occur, matter will persist much longer. Black holes will remain the final bastions of mass. But even they are not eternal. Through Hawking radiation, a quantum process predicted by Stephen Hawking, black holes slowly lose mass over extraordinarily long timescales. Stellar mass black holes would take about 1067 years to evaporate. Supermassive black holes would last far longer, perhaps 10, 100 years or more. These timescales dwarf anything we can meaningfully imagine, yet they are natural consequences of the laws governing gravity, quantum mechanics, and thermodynamics. The fate of the Sun, the solar system, and the Milky Way are chapters in this vast timeline. The story of our galaxy's future is therefore both intimate and immense. Intimate because it involves the fate of our own star and planet. Immense because it unfolds across billions and trillions of years, reshaping entire galaxies. The Sun will die not in a violent explosion, but in a majestic transformation. Earth will likely be consumed or rendered lifeless. The Milky Way will collide with Andromeda and change form. Star formation will fade. The galaxy will grow quiet. Yet this is not tragedy in a cosmic sense. It is evolution. Stars are born, shine, and die. Galaxies merge and transform. Matter cycles through generations. The forces that govern these processes, gravity, nuclear fusion, electromagnetism, operate without intent. They shape the universe through consistent laws. In contemplating the fate of the Milky Way, we are reminded that we live in a brief, luminous era. The sun shines steadily. The galaxy's spiral arms are bright. Distant galaxies are visible in the night sky. But cosmic time stretches far beyond this moment. The future holds transformation beyond imagination. And though the Earth may not endure those changes, the laws that guide them will remain the same. Gravity will continue to sculpt structure. Nuclear forces will dictate stellar lives. Electromagnetism will carry the last light across space. The Milky Way's destiny is not annihilation, but change written in the language of the universe's most powerful forces. Long after the Milky Way has merged with Andromeda, long after spiral arms have faded and star formation has slowed to a whisper, the story of our galaxy does not end. It simply enters a new era, one defined not by brilliance and birth, but by silence and endurance. The long cosmic fade is the final chapter in the life of a galaxy, and it unfolds across timescales so vast that even billions of years become brief intervals. In this distant future, gravity will remain, dark matter will persist, and black holes will dominate. But the light of stars, the engine of visible complexity, will gradually diminish. After the Milky Way and Andromeda merge into a single elliptical galaxy, often called Milkomeda, the violent interactions of their encounter will eventually settle. The gas that once fueled spiral star formation will have been compressed, consumed, or heated. A final starburst may briefly brighten the galaxy, but that flare will fade. What remains is an aging stellar population. Within this grand arc, the Milky Way's story is a chapter, a luminous and dynamic phase in an evolving cosmos. From its birth in the early universe, through its spiral grandeur, to its merger and slow fade, it embodies the interplay of gravity, nuclear physics, electromagnetism, and dark matter. The fate of the Milky Way Galaxy is not singular. It is part of a universal narrative. All galaxies will follow similar paths: formation, growth through mergers, star formation and enrichment, eventual quiescence, and long-term dissipation. The timescales differ, the details vary, but the fundamental arc remains. For now, we live in a rare era. The Milky Way is vibrant. The night sky is rich with distant galaxies. The sun is stable. Life flourishes on at least one world. The universe is young enough for stars to burn brightly and old enough for complexity to emerge. But the future is vast. The galactic clock will continue ticking long after humanity's time has passed. The Andromeda collision will reshape our home galaxy. The sun will transform and die. Star formation will cease. Black holes will reign. And eventually, the last glimmers of structure will fade. In the end, the Milky Way's fate is governed by the same forces that built it. Gravity gathers and merges. Nuclear reactions ignite and extinguish. Electromagnetism carries light until there is none left to carry. Dark matter shapes the unseen framework. The story of our galaxy is one of transformation. It began as a cloud of primordial gas. It became a spiral of light. It will become an elliptical relic. And finally, it will dissolve into the cold silence of deep time. The universe does not promise permanence. It promises change. And the Milky Way, our cosmic home, is no exception.